Our first speaker is Professor Meena Mahajan, and she will be talking about changing set representatives in different ways.
So when I was preparing for this talk, I prepared this title and I also had an abstract, but I see that abstracts are finally not there anywhere in the page. So this is the abstract that I prepared. But maybe now you don't need to read it because you will hear the talk. And so this is what I'm going to start with. We are familiar with words like this. There's a set of people, many people, n people, and every possible subset of those people, there is some committee which consists of those people and which is supposed to take care of some task. Okay? And every committee chooses a chairperson, one of the members of that committee. So if you want to use more formal notation, there's a set of numbers 1 to n. Forget people's names, you just give them numbers. And there is a chair function, C, which takes a subset and produces an element of the set. And of course, if the subset is not empty, then the element it produces should belong to the set. The committee should not have a chairperson who is not in the committee. So there's this committee manic world, and there is some way in which each committee decides to choose its chair. Now, committees can change. But if you have one committee and you want to change it into another committee, typically what you would need to do is remove some members who are in this committee but are not there in the new committee, and then maybe add some new neighbors. Okay, so that's a morphing one committee into another. And pictorially, I mean, if you have this gray set which depicts one committee, and then there is this, so that's the set S that I've mentioned abstractly, and then there is a different set T, which is the red set there. So then you take the part which is both in the gray set and the red set, those people you remove from the committee. The people who are in the red set but not in the gray set, you add them. So you get this picture on the right. The gray shaded region on the right is the new committee. So you change one committee to another by applying some different set. And you can apply many different sets in many different ways. These are all, just pictorially I'm showing some ways in which you can go from one committee to another by applying a difference like this. Now, when you change from a committee S to a committee T, the chairperson may change, may not change. So in particular, if the previous chair, the chair of S, is also in T, then of course the new committee has to have a different chair because that person has gone out of the new committee. But even if that chair was not originally not in the different set, the new committee after all is a new set of people, and they may choose to choose somebody else as the chairperson. So the chairperson may change even when the original chair is a candidate. And in fact, well, you may have a different chairperson even if the old chair is a candidate. So now the question we want to ask is this chair function, whatever way in which these people chose the chair, how sensitive is it? In how many ways can you change the committee to another committee and boom, the chair changes? Now choosing the chair is also a kind of fraught issue, so maybe there is some robustness that we want to look for. So in particular, what we are going to look here is how many disjoint different sets can you apply to a committee and end up with a committee which has a different chair? Okay. So some formal definitions which if you want you can look at them, it's not really essential. I can just tell you in words, block sensitivity of a committee S, the number of different sets which don't interfere with each other and which when applied to this committee change the chair. Okay. So that's what I have this definition here of the block sensitivity of S, the maximum K, so that you can find K disjoint, non-interfering ways of changing the committee S, and each change results in a new chair. And there's also a version called monotone sensitivity. Your changes should only consist of adding new people or should only consist of removing people, not doing both. Okay? So pictorially, if you look at this first diagram on the left, there was this gray committee and various ways of changing it. If I want to look at block sensitivity, if I include the brown block change, then I cannot include the red or the blue or the green change because they intersect, they overlap with it. But I can use the other blocks. So in the middle, there's this picture which shows that there are 5 blocks which are completely disjoint. And assuming that all of them give rise to a committee with a different chair, then I could conclude that the block sensitivity is at least 5. But if I want to look at monotone block sensitivity, then I need all the blocks to be inside, not only disjoint, but all of them inside or all of them outside. So this block is outside, but if I take that, I cannot take the guys who are inside. So you could have a completely different value, for a much smaller value for the monotone block sensitivity. Okay, so the question we want to ask is how large can this sensitivity be? How large can monotone sensitivity be? And here's what was known. Okay, yeah?
If all of them are outside, then it's not necessary that the chair changes.
It's not necessary at all. No, so you only count the maximum number of blocks that you can find which are all outside and which result in a committee change, in a chair change.
But you're only adding members, so how do you decide whether the chair changes or not?
You are given the chair function. So for a particular chair function, a block is sensitive if it causes a change of chair. And you're only counting sensitive blocks.
So just to clarify, there's a predetermined function from the power set to the set.
Exactly. Given a chair function, we are talking, it may be determined in whatever way, and we are talking about sensitivity with respect to that. But the very next slide will say that how that chair function is predetermined does not matter. The theorem is for every chair function. For every way that you may come up with of finding chairs of a committee, I can find at least one committee which is quite large, some constant fraction of the number of people in it, and which has square root n order square root, omega square root n ways of changing the chair. Okay? So it doesn't matter which chair function you use. For every chair function, there is at least one committee which is large and which is very sensitive. Lots. So with 1 million people, there is a committee which has like maybe 500,000 people, and there are 1,000 ways in which you can change the chair, and these 1,000 ways are completely non-interfering. So this was something which was shown 3 years ago by Goldwasser, Impagliazzo, Pitasi, Santanam, and they had a very complex, long-winded proof which used a lot of very heavy machinery in combinatorics and in algebra and in proof complexity. They used the sensitivity theorem, they used proof complexity degree lower bounds, trying to show that one is in the ideal of some polynomial equations. It was a very, very complicated proof. It was described by somebody I know as, proving something, doing something like this, putting food into your mouth like that. So what we were trying to do was to find a more simple, direct proof of this statement. This statement itself is very interesting and nice, but there should be an easier way of seeing why it is true. So that's what we tried. Who is we? We is myself and Arkadev Chattopadhyay, who is a TIFR in the computer science group. Yogesh Dahiya, who is sitting there. He's not giving this talk instead of, and I'm giving it because he's been very busy. He just submitted his thesis day before yesterday. So we were trying to simplify that proof. We did not quite succeed. But what we succeeded was in showing something which is similar but different. We showed that no matter what chair function you have, there will be at least one committee which is large, and in which there are cube root of n monotone blocks which change the chair. Either all cube root of them are additions or all cube root of them are deletions. This is something which was not implied by the previous result. This we could prove, and this we could prove by an extremely direct constructive argument. So, I'm very proud of the kind of direct argument that Yogesh came up with. The previous argument, if you want to see the full proof, somebody who does not have the background in this area but has enough mathematical maturity can sit and read the papers and understand the proof. It will take about 2 weeks. This I can explain to a similar person in 2 hours. So it's a huge change, and it's still giving something which says, omega n to the 1/3, not quite square root n, but almost there. So it's a very nice constructive argument which shows this. Okay, so this sounds like something combinatorially perhaps intriguing, but why should we even care about a question like this? So why should we care? In the next 2 slides, let me try and explain this. Here's a different committee-related question. It's not about chairs at all. Okay? So there's a very large committee which is meeting inside a convention center. You are outside. You are not one of those n people at all. And you are trying to slip across a note with some confidential information to one of the committee members. You have no idea which committee is meeting. So how are you going to get a person to come out to the door to take this stuff from you? Well, you pull out your phone and you call one by one, are you inside? I want to give something. He says, no, call the next person, and so on. How many calls do you need to make? So this is what we call the find one problem. How many calls do you need to make till you find somebody inside? If the committee is large, let's say half the people are inside, n by 2, then n by 2 calls should be enough. If you're super lucky, your first call itself is enough. You have found somebody inside. But if you're super unlucky, the first n by 2 guys say no, 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 and then everybody else is inside. So you may need as many as omega n calls in a deterministic calling strategy. But then maybe we want to use randomness. Randomness we use all the time. Why not here? If you're willing to use randomness and tolerate some error, some failure, okay, I couldn't find anybody inside, just 10 calls is enough. It doesn't matter how many people are there inside. With 10 calls, the probability that you will fail is down to 0.001. This is a pretty good way of finding somebody inside. Okay, so we have a way of solving find one and using randomness. Some small chance that there is error, but the error chance is very, very small. Now, the story continues. You have identified one person, you have passed on the material to him, you go away, now your colleague has to give something, finds some addendum to be given, and would like to pass it on to this meeting inside. So your colleague wants to know whom should I call to give this material to, but you can't reach your colleague. A typical signal problem, you can't get through. So what can your colleague do at this point? Where your colleague can again, use randomness, make 10 calls and find somebody inside. But the person your colleague finds may not be the person you find. And when we're talking about this committee which has 500,000 people inside, to give these two pieces of information to two different people is essentially useless. You want to get the same person. Now what can you do? So this is the kind of algorithm that we call a pseudo-deterministic algorithm. A pseudo-deterministic algorithm or a pseudo-deterministic strategy would be one which it can use randomness to decide what to do next. But finally, when it gives the answer should be the same across different random runs. Or if not the same across all different random runs, at least across most of the runs. Most of the time, it should return the same answer. That would be a pseudo-deterministic algorithm. So now for the same committee related question, we can ask, how many calls do you need to make to get this canonical one person inside to solve this find one problem? And what these guys showed 3 years ago, the paper that I mentioned by Goldwasser, Impagladze, Pitasi, Santanam, they showed that the block sensitivity of this chairperson problem is large, and that implies that solving find one pseudo-deterministically requires square root n calls. So 10 calls was enough to find any one person, but if you want to find the same person repeatedly, then suddenly it goes from 10 calls to square root n. And in fact, they believe that it even goes all the way to omega n. But that they were not able to prove. That is something that we also tried and we were not able to prove, so that remains open. Pseudo-deterministically, exactly how many calls do you need? And this find one, I mean, okay, it sounds like a very cute thing, there's a convention and a committee meeting inside, but why is it important? Well, it turns out that it is the hardest problem in a certain complexity class. That is a class of problems which are solvable using queries which are chosen in a non-deterministic way, and you're choosing only polylog n queries. It has a technical name, it's called TFNPDT. That's not important. There is a complexity class which is reasonably significant. People have looked at it in many different contexts, and this find one problem is complete for that class. So anything that you can improve about the query complexity for find one will have implications for other problems in that class. So this is what we are looking at, and this is all I have to say. Thank you.
Are there any questions?
So how significant is this gap square root n versus cube root n in terms of applications and so on?
In terms of applications, we don't know. So specific applications of the fact that the monotone block sensitivity is large. We know of settings where the monotone block sensitivity being large means different things, but not in this setting. So we don't really know. It's combinatorially something nice, but we don't know what it means.
Is there a way of mapping this problem into a familiar problem?
Familiar.
Satisfiability.
Oh, I see. No. So these are problems which are computationally very easy. The hard part is that you are saying that calling is costly. Because the kind of thing that you look at with satisfiability, a computational question, you are told what is the committee. And then you try to find out something about it. But then it is trivial to find one member there. So this is query complexity, and this is a whole line of work which says, in query complexity, it is much more easy to prove that things are hard. Why would you be interested in query complexity? Say you're going to the bank to try and get a loan. Then the bank staff dealing with you will ask you some questions. And maybe they have a set of 100 questions, but any one person rarely gets asked more than 10 questions because the next question depends on the answer to your previous question. Or medical diagnostic, you're being asked questions in an adaptive way. The whole set of questions is very large, that is the N that we're talking about. But the actual number of questions being asked to any one individual or on any one input is typically much smaller. And we would like to bound that. We would like to say that the query complexity is small. So these are settings where we are interested in query complexity. And that's the setting here. It turns out that in query complexity, it is easier to show that things are hard. And there are modern lifting theorems kind of in that framework which say that if you show that something is hard in the query world, then a transformed suitable version becomes hard in the computational world. So eventually you can get to something like what you're saying, satisfiability being hard, but it's a long stretch there. It can be done, it has been done in select cases, but it's not that easy to state. But query complexity itself, I would say the reason why it is interesting is in these kind of human interactions. How many queries would you need to ask?
Any other questions?
So you were also able to get this omega cubed root of n calls?
We were able to get cube root of n.
Even for pseudo-deterministic?
No. So we are not looking at the algorithms at all. We are only looking at the sensitivity question for the chair function. And so I think your question is similar to what is being. So because we have a monotone block sensitivity bound, what does it say about pseudo determinism? We don't.
If you have cube root 10 and someone has square root 10, maybe possibly smaller numbers will be eventually found, or it will not get better than this?
No, we want bigger numbers.
Sorry, the other way around.
So bigger, yes. I mean, the authors of the previous work believe that the correct answer is omega n.
But is there some?
Is there some way? We don't know. And I don't know if Yogesh has a different answer that you want to add. I don't know. Okay.